Any questions? Forget to do. Okay. So, sort of picking up where we left off. I have a spring there, to which I've got the rubber bands around this time. Last time I didn't have it set and fell, and I took a guess about where it was. This is in case it falls, I don't have to think about how to put it back, because if I have a different number of coils there, it changes basically the spring constant. I went ahead while you were taking the test, I applied certain masses to it and measured the position of it from the ground, and it pops out like this. Pretty close to linear. So the question is, what is the spring constant? Or how would you find it? When I attach a mass to the end of it, what are the forces acting on it?
Gravity. Weight.
Yep, that's it, weight. And?
Tension. Or spring force.
Yeah. So I have those two forces acting on it. And what's the spring force equal to? Or let's just go through the process. Got the force diagram. And if it's just hanging there in equilibrium, what's the acceleration?
0.
So choosing our positive direction is completely arbitrary. Which way do you want to make positive?
Up.
All right. Nothing to break up. So what's the equation of motion?
Spring force minus the weight equals 0.
All right. And we can manipulate that. The spring force is equal to the weight. Substitution. What are these equal to?
K delta X equals mg.
So K, our spring constant, mg over delta x. Now what?
Plug and chug.
What would you plug in?
Delta X mg.
All right, we have several delta x's from which to choose. Corey?
I was going to say just measure from the top to where the weight is hanging in.
Oh, do measurements from the top? So don't do x, actually do a delta x, okay? So that would be 0, got that one done. What would be the next position? Or changing position, really. Or displacement, as some people say. Or how would you find it?
Position final minus position initial.
Okay. So this right here,
Be negative 113, I think.
say it again.
Negative 0.113.
All right. Next. Negative 0.289.
Yeah.
All right, and the last one?
Negative 0.563.
negative 0.573,
6.3.
63. Okay, now what?
Pick a delta X and plug in the mass for that specific, like, row that it shows.
To come up with 4 different values?
Yeah. Take the average of them maybe.
Okay, that's one approach. Another approach is actually to look at a slope here. First off, what does the negative sign here indicate?
That it's moving down.
Okay, it's a direction thing. We've already taken the direction into account here, so we really don't have to worry about the negative side at this point. So if I plotted it without the negative sign, so let's sort of plot delta x, the absolute value of the displacement in meters. We end up with, so 0, 0, and 0.11, so 0.02, 0.113, 113, so somewhere around there. Then 0.05, 0.289, we could put it about here. A little bit lower. And then 0.563 and 0.1563, somewhere around there. What's the advantage of actually looking at a slope instead of individual points?
Could individual points be affected by like an outlier, and the slope would be like the entire system that we did?
Yeah, in essence. The general assumption is that on our measurements, we're a little bit high on some, a little bit low on the others, and this sort of washes out those sort of fluctuations. It can still be thrown off by an outlier, but how much depends. So if I take the slope then of this, which for some reason decided to pump. So if I looked at the slope of that line, how would I use that in my equation over there?
You could plug it in for m over delta x.
Okay, except is our slope m over delta x? Basically, shook your head no.
Delta X over M, right?
Yeah, it's rise over run, so it's delta x over m. So as Daniel said, we will substitute for here, but this is the reciprocal of the slope. So k is going to be the slope times the acceleration due to gravity. And the slope, which I also happen to do, 5.64. 5.64. What would be the units of the slope?
Meters per kilogram.
Say it again.
Meters per kilogram.
All right. Times, for what we're doing, 9.8 meters per second squared. We've got something off here. Let's see, we got G. No, that's right. Divided by that, that's right. Oh. I just contradicted myself there. This is G divided by the slope. So 9.8 meters per second squared over 5.64?
I think so, yeah.
5.64, and that was meters per kilogram. So what do we get?
Meters squared per kilogram second squared. Oh, it's, never mind, it's, second squared per kilogram.
Sorry, what is it?
Is it second squared per kilogram?
Flip it.
Kilogram per second squared.
Meters per second squared divided by meters per kilogram is a meter per second squared times a kilogram per meter. So kilogram per second squared, or newtons per meter. Okay, so we have a rough estimate of the value of K there, or it's not too rough, I mean, some precision. So K, 1.738 newtons per meter. This stuff right here we did last time. So what I'm gonna do is I'm gonna add 50 gram mass. And we are going to predict what the period's gonna be. So I should be able to pull it down, let go, it's gonna oscillate back and forth. And so the question is, what should the period be with the 50 gram mass there? Or how would you find it? What's the symbol for period?
Capital T.
Capital what?
T.
I assume you said T.
Yeah.
Should have known. There are certain letters, F and S, I sometimes have difficulty hearing the distinguishing between this, especially when my wife says it.
The square root of mass over the square root of the square.
And what's the mass?
Did you say 50 kilograms?
Say it again?
Did you say 50 kilograms?
50 kilograms would have, that'd be huge. It'd be touching the ground if I were doing 50 kilograms.
Is it 0.05 kilograms?
Yeah, 0.05. It was 50 grams.
Oh, okay.
If I said 50 kilograms, well, there's recording of it, so it was unintentional. 0.05 kilograms divided by our spring constant, which we just found out, 1.738 newtons per meter. So what is our predicted period of this oscillating back and forth? 181.
Yeah, seconds. I forgot the square root.
Yeah, square root's rather critical there.
One point zero seven.
1.07 seconds. All right. So let's find out how well this comes true. I'm going to extend it down a certain amount, and then I'm going to let go. Now, in our formula, when we derived it last Thursday, how far we stretched it was not part of this. If you recall, when we were solving for it, the amplitude got canceled out. So I can set whatever amplitude I want. And I'm going to take it down about 10 centimeters and let go. All right, so I need help with timing here. About 10 centimeters. I'm going to do 3, 2, 1, go. When I say go, I'm going to let go. We're going to time 10 oscillations. And one oscillation is up and back.
So how many times it bounce, baby?
Excuse me?
So how many times like it angles?
Yeah, it's going to go up and down 10 times. We'll time that and then divide by 10.
Okay.
All right. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what times do we have?
14.63 seconds.
14.63.
14.32.
14.13.
Clearly mine's not that.
14.32.
Yeah.
Is that it? So let's get the average of those. Got the 14 part.
14.35.
And that was for 10 oscillations, so that would give us a period of 1.435 seconds, which is 40% off of what we have predicted. Now, sometimes we get the physics demonstrations that just are 40% off, and that's just the way it is, but I actually expected this one to be off. Why is it that that and that do not match? Or even close to matching?
We didn't account for air resistance.
Air resistance will be minimal at the speed it's traveling.
Is it not a perfect spring?
Yes. The thing that we are not taking into account, the fact is the spring has its own mass. Our ideal spring does not have mass. So what we need to do is somehow figure out what is the effective mass of the spring. So let's do that. So what I'm going to do is I'm going to take the 50-gram mass off. We're going to find the period of it. I know the period is equal to 2 pi times the square root of m over 1.738. We're going to do 10 oscillations of just the spring itself, and we'll solve for the effective mass of the spring. Let's get that off. All right. Those who are timing, please get ready. All right, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10.52.
10.52.
I got 10.51.
10.43.
10.27.
10 point,
27.
there was another
10.10.
one.
10.10.
10.10.
10.62.
All right, what's our average? The first two there got me hoping that we got this really nice tight cluster.
got 10.38.
So that gives us a period of 1.038 seconds of just the spring by itself. Just coincidence, it's somewhat close to that. If that's my period, what is the effective mass of my spring? So if we plug that in for T, or something.
Oh, 474
Units.
kilograms.
All right. So we have this effective mass of the spring, so no matter what else we add to it, we have to take that into account. And so our prediction over here needs to change a little bit. This is equal to 2 pi times the square root of 0.05, which was the mass we added, plus the effective mass of the spring, 0.0474, divided by 1.738. And what is the new prediction? Units?
Seconds.
And we had gotten 1.435 experimentally, and we have a prediction of 1.49. So not too far off. Questions?